So let's get started. Hope everyone had a good weekend. Today's Halloween, so happy Halloween. Try to stay safe tonight if you go trick-or-treating. I know you're all not old enough yet to not go trick-or-treating yet. So, yeah, but have fun. Enjoy your night, but don't definitely be safe, especially driving and stuff like that. Yeah, so let's get started. So, again, today's office hours is normal. Lab 7 is due tonight. So come by office hours if you need help. I made it tonight so that you can have plenty of time to ask questions and stuff. And then homework 2 will be posted on Wednesday. And it'll mainly consist of, I'm going to give you the solution for Lab 7. And I want you to write like a page or something summary or kind of a detailed summary on what it does. What each script does, what the makefile does, whatnot. So you can kind of study that script and look through it and stuff, write up a little, not necessarily an essay, but just a description and summary on what the lab does. Because I know the lab was hard, so I'm going to count it as a homework grade to explain what the lab did, as well as the lab itself, what you turn in tonight, will be counted as a lab grade. So if you don't complete it, it's not a huge deal. It's mainly going to be, hey, did you try on the lab? But it won't be like critically like picked apart to make sure you did every little thing right. But homework 2 will be you explaining what it does so that you can actually dig into it and kind of learn what the homework or that lab last week actually does, why it's kind of somewhat intuitive, and why it's useful. So. One thing I didn't put on here is the midterm should be posted tonight or tomorrow. Probably tonight. I'm going to try to grind through the rest of them and get them all graded and put in tonight. So I'll be busy as well. Hopefully that won't frighten too many of you on Halloween. Yeah. What? Probably in a week or so. But then next week I'm going to assign a new homework. So it's going to be homework for a little bit. But after that, you'll probably have 2 weeks on homework 3. So I'm just trying to get enough homeworks in to justify the 20% of your grade. Okay, so what's left in the course? We saw this last week. There's 3 more lectures and labs. The 4th week, so there's total in 4 weeks left of the course, but 3 weeks we'll be actually learning new stuff. So next week we'll learn about Git and GitHub and version control and collaboration. Then the following week you'll learn a little bit about customizing the shell a little bit more to make it more personally good for you. And then the last week is review for the final. And then the very last week of this class, which is the 4th week, that's left, is the final. So you won't actually have a final on finals week in here because it's not scheduled for the class. So the last week of the class will be your final. And there'll be 2 parts, just like the midterm. The first part will be multiple choice or written. I haven't decided yet. That will be on the Monday. And then the second part will be a lab. Like you'll go into the lab and do it for that allocated 50 minutes that you usually have. And then you'll turn it in and that's it. That's the rest of the class. So, and you'll be prepared for what we're going to go over. So today we're going to go over processes and jobs, and we're going to go over a little bit of like computer architecture kind of topics on how computers actually run programs and things like that. So programs run for the most part on the CPU, or central processing unit, and that's what you can consider as the brains of the computer. So, brains. Brains, good old Halloween already. So, pretty fitting. So programs can run in 3 different styles. They can run in serial or sequential mode, concurrency, or concurrently, and in parallel. So up until now, you've probably only experienced serial or sequential programming, where your program, you compile it or you run it, and it runs start to finish, right? And for the most part, during my undergrad, that's the only programs I wrote, except for a couple that required threading and some multiprocessing. But for the most part, you're probably going to be more familiar with serial programming, which is old, and it's not the most efficient, and there's disadvantages, but there's also a couple advantages as well. So yeah, concurrency is a little bit different from serial in that you can run multiple tasks at once, but you can only really make progress on one task at a time. And in parallel, you have multiple tasks that are being done at the same time, exact same time. All right, so serial processes, like I said, they kind of go from start to finish in one run, right? So this is what you're used to for now, is you start your program, you end your program, you're done. So it's just one line of just start to finish. You can't do anything else. And the problem with this is it ties up computer resources. So if we did everything sequentially or serially, then nothing else can be done at the same time that your task is being completed. Think of if you have a one-core CPU, it can only handle one task at a time. And then you can't run the operating system things and whatnot. So for the longest time, this was like early in computers, you could only run one thing at a time, and that's it. You cannot run anything else. Nowadays, this is different because you have an operating system, you have all kinds of things layered on top of each other that are running at the same time or concurrently. All right, so then we get to concurrency. So concurrency allows you to kind of do what's called context switching. So there's several different methods of context switching, but you basically have a ton of different tasks that need to be completed, and you switch between them as they need to be done. So instead of just doing start to finish, now you're doing things out of order. So you start a process or a program, you stop and pause in the middle, then you do a different thing to try to get it done, and then you get done with that, you pick up where you left off on the other process or program. So you have something like a program called T1, you pause and say, okay, I'm going to complete T2, and then, okay, well, there's this one called T3, and then, okay, you get done with T2, you start T3, and then, okay, well, you pause T3 to do T4, and so on. So you're kind of switching between tasks to try to complete different stages of them. And there's multiple different kind of methods or approaches to doing this. One is round robin. So you do, if you are familiar with round robin from like 145 or 146, you do a task for a set amount of time, then you switch. You do the next task for a set amount of time, you switch. So do program one for 1 millisecond, then switch to the next one, do it for another millisecond, and keep switching until you eventually get done. This is not really great in practice. Instead, most operating systems and programs opt to use something like a priority queue or shortest to longest approach. So you do, in a priority queue, if your operating system has a program or task it needs to complete, that takes precedence over something that's not as important as the operating system task. Shortest to longest is you do, okay, this task is going to take the least amount of time, so I'm going to get all of those done first, and then I'll do the last ones last, or the longest programs last. All right, so, but there's this idea called pipelining. So pipelining is basically you want to maximize your compute resources. If you do things serially, then you're going to have parts of your processor or CPU or computer that are just sitting there idle doing nothing. So that's not very efficient because they're just sitting there doing nothing. So think of when you're doing laundry, you don't go and put your load of laundry in the washer and then wait for it to be done and then put it in the dryer and then wait until the dryer gets done to put in your new washer. No, you put washer, once those done, you put them in the dryer, and then once you've got those in the dryer, you put another load in. So you're using the washer and the dryer at the same time. So computers do something similar, where one program or task might be using this part of the CPU, but then another task come along and you can say, okay, it can use this other part of the CPU. So you don't have just resources sitting around doing nothing, idling and whatnot. So think of the washer doing laundry in this case. You have washer, dryer, and then you're folding all at the same time. So this is the most efficient use of resources. Okay, so then we get to parallelism. So this is when you have multiple tasks that can be ran at the exact same time. So you have, say, multiple cores in your CPU. You have core 1, core 2, core 3, core 4, and they can all be doing different things at the same time. So you can accomplish many different tasks at the same time, and this increases throughput. So you can give it tons of tasks, it computes all of them, finishes them all a lot quicker than giving them all just into one core to compute all just in serial. Because you, again, have to wait before the first task if you do things in sequential mode. Whereas in this way, with parallelism, you can do task 1, task 2, task 3, task 4 all at the same time. Okay, but there's a balance to this. Right? It's a balancing act, and that you have to kind of balance throughput versus speed. So in most cases, when you do a sequential task, it can be done faster rather than doing a ton of things in parallel. So when you do something sequential, you can think of it as on the CPU, you have a highway that's a mile long, and that highway is 1 lane wide, and you're going 80 miles per hour. That's the speed limit. So you have a bunch of cars going through there really fast sequentially. Whereas parallelism is you have a multi-lane highway, so you can accommodate more cars, but the speed limit is slower. Right? So it's going slower, but you're getting more cars through. And this example actually works over to hardware too. Most sequential hardware is much faster at doing sequential things and getting one thing out quickly than doing things in parallel. But in parallel, you can get more things done in a little bit more time. So say you have, let's see. Say you have a process and it's sequential, then you can do it faster from start to end than you can do it on a 4-lane highway. But if you have 50 different tasks, you can do those a lot faster in a little bit longer time than one thing takes on the CPU or sequentially, but you can do a lot more of them in that span of time. So there's a balance to parallelism versus speed, or throughput versus speed. So let's do a quick abstract thought experiment. So can humans do things serially, concurrently, or in parallel? This is a question for y'all. Anybody want to answer? Yeah. Serial? Yeah. So we can kind of do things serially and concurrently. We can't really do multiple things. We can't look left and right at the same time, right? That's parallel. But we can do things kind of serially or concurrently, more leaning towards serially. So you can focus on one thing at a time and do that one thing at a time and get it done. You can do things concurrently in that, just like laundry, you can put stuff in the laundry, put stuff in the dryer, and fold things all at the same time, but you can't do them all at the same time. So this parallel idea, humans can't really do on their own. But how can humans do things in parallel? Well, humans, right? So you can have multiple people doing things at the same time together to accomplish something in a lot less time. So think of coding. So if you have this huge project, typically, if you're all good computer scientists, which you all are, you'll do things in parallel, and then you get things done quicker because there's more of you that can do things and do computing in your brain. So that's how humans can do things in parallel, is add more humans to the problem. But one individual human cannot do things in parallel necessarily. Okay, so this brings us to the computing examples. So CPUs, so those are your processors, your Intel i7, i5, whatever, Ryzen 9, Ryzen 7, whatever, typically have 4 or more cores. And each of those cores can do its own program or things sequentially. So it used to be 10, 20 years ago that you would only have one core CPUs and they could only do one thing at a time, but they could do them concurrently. Well, now we're increasing parallelism by increasing the number of cores, so each core can do a different task. Does anybody know what hyperthreading is? So the idea, if you've heard of hyperthreading at Intel CPUs or whatnot, this is just pipelining. So hyperthreading is just pipelining, basically. You have this chunk of hardware and this chunk of hardware in this one CPU core, and you can use them concurrently in that you have one task on one chunk of hardware and the other on another. So you're maximizing. That's what hyperthreading is, if you've heard of hyperthreading. Not important otherwise. So again, CPUs are good for serial tasks. Again, we're increasing the parallelism in them, but they're really just meant for general compute tasks. Encryption, decryption, doing simple math, or very complex math. But they're kind of limited in how big the cores can get, because they're what is it? They're good at everything, like good. They're not excellent at anything though either. They're masters of none, right? Good at everything, masters of none. So they're good for concurrent computation. They're good and very fast for serial computing. And then you've got GPUs. So GPUs, they can have thousands of cores or compute elements, and they're good for simple math tasks. They can't do nearly what the CPUs do because they're not generalized computing units, but they're very good for parallelism on very simple tasks. So if you don't know how a GPU works, GPUs are what makes your image on your screen come through. So each of these images or pixels that are on your screen have to be computed. Everything has to be computed. So this, if I turn the image or something like that, the GPU has to go in and compute your angles and whatnot of how to turn it and whatnot. So it's good for simple math tasks, and it can do it very quickly in parallel. And then there's more architectures always coming. So there's TPUs, there's a ton of different computer architectures and accelerators that are coming out. My lab actually works on a couple of these, but yeah. So these are your two basic ones that you'll see most often is CPU and GPU. One's good for sequential concurrency and running general things. The other one's good at very simple tasks and parallel computing. All right, so here's your CPU. If you don't know what they look like, they have their little chips. They go into your motherboard, and then this is your GPU, so a lot bigger. And usually your GPU will use a ton more power than your CPU because you got so much more compute elements and cores. So, all right. So now, how do we apply all these things? So there's an idea of processes and jobs in operating system. And these processes and jobs are just simply programs or commands you run. So for a job, it's usually a command like find, grep, cd, ls, etc. And then, or a shell script, or even just a program that you launch in a language. So these are all jobs, things that you can run. All right, so how do you process, or how do you actually launch and check jobs and put them in the background or foreground? So by default, all jobs run in the foreground. That means they run in your terminal, right? They output things to your terminal and whatnot. But you can also run things in the background. So if you want to run your job or thing in the background, you just do an ampersand at the end. So if you want to run a script in the background, you do script.sh ampersand, and it runs it in the background. So you can keep using your terminal elsewhere. So let's see. If I do something like sleep 50. So sleep just has a loop for 50 milliseconds, yeah, or 50 seconds.
So what will happen if you use like vim and then like a file and then an ampersand?
It will probably launch it in the background, and then you have to kill it because it's interactive. It might not even let you do it if it's an interactive program. So if we do something like sleep 1, it's timing 1 second, and it basically for that 1 second you can't do anything, right? It holds up your terminal because it's running in the foreground. Whereas if you do sleep, let's do sleep 5, or not 55, sleep 5, then I can't do anything for 5 seconds until that command gets done because it's running in the foreground. In order to do something else, I'd have to open a new terminal or a new shell. But if I do sleep 5 ampersand, then it launches a job and gives me this job ID, and in 5 seconds it's going to tell me that it terminated. So it says, hey, it got done. It's done running, right? So I could have kept, during that sleep 5, I can keep doing stuff. ls, clear, clear, and then it says done. I can still keep using my terminal even though something is running in the background. So it just makes it to where it runs in the background. So let's do sleep 10. So if I do sleep 10 ampersand, so let's say I launch that job and I clear and I don't remember the ID. Well, if I want to see what's running, I just use the jobs command. And it says, hey, this job is running. And it says, okay, well now it's done. If I do jobs again, there's no jobs because nothing is running in the background. All right. So that's jobs. You have foreground jobs that prevent you from doing anything in the terminal until it's done or until it terminates. And then you got background jobs that will just run in the background and allow you to keep doing things in your terminal. And then you've got 3 different states. You've got running, stopped, so that means terminated, or suspended. So suspended just means, hey, it's paused, you can run it later. And you can change all these things. I almost never deal with jobs. I deal with what's called processes. So yeah, these are ways you can change how jobs are run. If you want to bring a job to the foreground that's in the background, you can use FG. If you want to put a job into the background, you have to suspend it or pause it first, then put it in the background and launch it in the background. Or if you want to suspend them, you use Control Z to actually suspend your job. So if I do something like sleep 10, press enter, and say now I want to put this in the background, then I do Control Z, and then it says suspended the job. So I did jobs. You can see that it's suspended. Now I want to finish running it in the background. So I do BG and then %side1, and it continues where I left off. So in the background. And it's done now. Okay. So for the most part, I don't really use this. This is just for your knowledge. I probably won't test you on this very heavily other than to know how to launch something in the background. So just remember ampersand. But yeah. But the problem with these jobs and processes is that if you accidentally disconnect or quit your terminal, those jobs are connected to your terminal. So if you quit it, then it ends the jobs. All the jobs that you launched in this terminal right here are done. They get terminated because you exited that terminal session. So in order to make them independent of the terminal session, you have to use no-hup, which stands for no hang-up. So if for some reason you're trying to run something on the Linux Labs remotely, and all of a sudden the VPN crashes, like it usually does, then that thing is terminated. Your program has been terminated, unless you put no hang-up before it. And then if you do, if the VPN does crash, then it will continue running in the background, even if you disconnected from the labs. So you can launch these things in the background and make it to where they don't actually terminate unless you explicitly terminate them or if they finish running. So yeah, no hang up and ampersand are important things if you're trying to run something remotely and for some reason your Wi-Fi gets cut off or something like that. All right, so what's the difference between a job and a process? So a process kind of is a job can be a process, but not all processes are jobs. A process can be an operating system task. It can be anything that you're running or whatnot. So a process can be like a system process where it's running the GUI, it's doing memory management, it's doing things, authentication, remote sessions, etc. But then there's user processes, which are things that you run, right? And these processes are not necessarily the same thing as jobs, but they're very similar. You can see your processes by doing something like top. So on the Linux Labs, you'll have top, and you can see exactly what processes or commands. You got these PIDs, which are process IDs, and you can see exactly in real time using top what's using your CPU, how much time it's been running, how much memory it's using, etc. Now, what I like to use, and it's not on the Linux Labs, is htop. So it's just human readable top. So this shows you like a little graph of how much of your processor or CPU is being used, how much memory or RAM you're using, and you can scroll through these. So you can see that you have this user. So I'm running all these things, but then if you scroll down far enough, I'm running a lot of things, you'll see all these other users. And these are the other processes that are running by root. So there's a root user, which is really just the operating system is running things. So it's running a ton of things to make your operating system work. If they didn't if the operating system wasn't running things, then it wouldn't be an operating system. It's not managing things like hardware and processes running. So this goes back to up here, where you have parallelism versus concurrency. So your operating system's running things in the background on the CPU, and you're running things in the foreground, and all these things have to be orchestrated. So that's what the operating system does, is saying, hey, this program can run with this amount of memory. Okay, well now an operating system task needs to be done, so I turn that process off, and I turn this one on, and it does all this orchestration. So that's what an operating system actually is doing, is it's just looping and orchestrating all your tasks and processes and jobs and whatnot. And it can do the balancing and all that stuff for you. Okay, so you can run the, check what processes are running with top or htop. It gives you the utilization. You can see what processes are running in your current terminal by using PS. So in this case, I'm just running my Z shell or shell, which is the terminal. Or if you want to see all processes for your user, you do -u or PS-u and then your username. Mine's this. And then it returns all the processes even outside of this terminal that are running on behalf of my user. Okay, so again, these are things I'm not going to necessarily heavily test you on, but it's good to know so that you can always kill something that's misbehaving or something like that. So if you have like something you launch or a program or script that you launch and it's an infinite loop and it's running and running and running, then you exit your terminal and it's still running, then you know how to kill it or take care of it. You can look at it with PS or PS-u, and then if you want to kill it, there's a kill command. So you just pass in the process ID or whatnot, or even the command that you want to kill, and it kills it. It just says, hey, you're done, terminate. Like, stop, I don't want you anymore. Okay, so that's processes. So it's like an operating systems topics more than anything. But this is also applicable to Windows, Mac OS. All of them are structured in this like process job kind of way that switches between processes and computes certain things and whatnot. All right, so that was the boring part of the lecture. Now let's do some C++ coding. So this is what lab's going to be on this week. C++, not jobs, not processes. I might have you run them just to put them in your brain, but for the most part, this is what lecture or lab's going to be on this week. All right, So, if you're familiar with programming languages, especially Java, let's go to my desktop. Let's do make directory demo, cd demo. If you're familiar with Java, you obviously can't code everything that you need to do things. You have to use some kind of standard library or some kind of pre-built code to do things. You can't just use, I mean, you can code it all, but it's a pain. It's like coding how to add, right? Simple things like that. So oftentimes you have to include or import standard libraries. And the way you do this in C++ is you use this include with the hashtag. So you do hashtag include, and then whatever package you want to include, as long as it's installed. So in the case of standard libraries in C++, if you want to print or take in input for the program, you have to import the IO stream library. So this is just, if it's a standard library, you just do angle brackets around it. So I'll open a file. So I'm going to do vi. Let's just do main.cpp. If I want to import to where I can print and take in things, I just do include IO stream. And that's it. So you imported IO stream, which we'll see what it does in a second. If you have your own custom library, which includes a header file or whatnot, functions, classes, whatever, you do something like include the name of it with quotations. So if you have a library, then you have to use quotations. If it's a standard library, you put angle brackets around it. Okay, so we don't have a custom one. Yeah.
Just to make sure, IO stream is for like reading stuff from a file? Or
Yeah, not reading from a file, but it's for like reading things from the terminal, asking the user for input, printing things to the terminal.
It's Java util scan.
Yeah.
Okay.
Or system.out.println or print.
So you need that to have a print?
Yeah. Yeah.
Okay.
So I mentioned system.out.println. So that's the way to print something to the terminal in Java. In C++, it's cout. So Java sucks, is what this says. But you have to do std cout, like this. Yeah, so this is the long way of doing it. This is very verbose and saying, hey, this is part of the standard library. That's where it should be. You do std : cout, and then you print whatever you want by doing like left arrows. So this is, think of standard redirecting standard input. And then you do your like little statement. So hello world. And then if you want to add an inline, you can do this. You can do std : inline. But this can sometimes be costly, so instead you can do just the new line character, like that. So you're using a library with the standard library that's got cout, which is an IO stream, and you're printing a hello world. So that's importing libraries. All right, so in Java, you use what's called methods. I hate the word methods. I don't know why they teach you methods, because everything like mathematics calls them functions, and most other languages other than Java calls it functions. But a method and a function are the same thing. You have some kind of function that does some things, and it takes in parameters and gives you output. That's what a function is. Same thing as a method. They're just called two different things for some reason. So in C++, just like I think Java has, they have a main function. So in order to define the main function, you just do int main, some parameters that if you want them, and you put brackets, just like Java. Very similar. And usually the convention is to return 0 if things went successfully inside of C++. So your main function in C++ should return 0. It's just a thing. It basically says, hey, it ran successfully. Otherwise, you can return anything else, and it will print an error. So if I do return 0, let's see what this does. So let me get rid of this line real quick. So if I do G++, main.cpp -o aprog, oh, I missed something. So I'm compiling this code, and it gives me this aprog, the program. It prints nothing. It succeeded. But if I change it to return 1, it's going to give me an error. So go back to my G++ to compile, and now if I run aprog, well, it should give me a error. But anyway, whatever you return out of this main function has a different meaning at times. In this case, it doesn't really care, but yeah, in a lot of cases, whatever is returned from main can result in an error or whatnot. Yeah. I've never tried. It's just whenever you do a main function in C++, oh, this is also going to get an error because you can't return and have a void function. Whatever the function type is, so if it's int main, you have to return an int, or else the compiler will say, hey, you are not returning something in a void function that's not supposed to return anything. But if we do void main, then let's see what happens. Yeah, it throws an error. The compiler's like, no, it has to return an int. So, yeah, it has to be int main. But, yeah, so you declare your functions like this. You have some parentheses. Inside the parentheses, you specify any parameters that you want to pass in, and then you do some things with it. All right, so that gets to compile. So compiling is the step that you're not used to, or used to doing manually at least. In Java, you have an IDE, you press the run button, it runs it, it compiles it, and then runs your actual program, the binary code or whatnot. But in this case, and especially in 240, you'll actually have to be compiling have those steps separate. So you write your code, you compile it, then you run it. So this compiler is what looks for syntax errors. So if you mistype something like I did earlier with include, it'll say, hey, you're not a good coder, fix it, kind of thing. It yells at you. The one thing that, and I misspelled semantic, it should be an E. The one thing the compiler will not give you is semantic errors. Semantic errors are logic errors. So like if you want to check if a value is greater than or equal to 0, and you only put a greater than symbol, then your compiler will not tell you that you're wrong. So it puts a little bit of trust into you to know what you're doing as far as your logic. And in some cases, semantic errors will happen at runtime. So if you're trying to access a value in an array or a list or whatever that's outside of the list, then it will give you a segfault error because you're trying to access something that's not there. So that's a semantic error. So compilers are really just, hey, the first stage of them is like, hey, did you actually code something valid? The next part of the compiler then compiles it into your binary or to specifically your assembly first, and then it converts it to binary. So, all right. So I'll do a quick hello world example. So if I do rm aprog, I do vi main.cpp, and I change void main, because we can't have void main, and we do std cout, and then say hello world, and then I'm going to put this at the end for a new line, and then I return 0. It will also give you an error if you declare. The compiler will also say, hey, if you have an int main and never return an int, then it will also say, hey, you didn't return anything. So we have to return something if you have a type here. All right, so let's compile this. So I just wrote the high-level language. Now we're going to compile it. So we do G++ main.cpp. And before we actually compile it into the actual executable, I want to see the assembly code. So if I do -s, it gives me this S file, this main.s. And if you look inside of this, these are the instructions in assembly. So this is why high-level languages exist, is because you have to convert all your language into assembly code, which is then converted into binary. And imagine you having to write all of this for that short little program to make it work. This is assembly. This is very close to hardware. And imagine having to write all of this for just a simple hello world. Right? And I'm sure you can make this shorter with the compiler, but the compiler or the x86 code to make this run, or actually this is ARM code, because I'm running on a MacBook. Imagine having to write all that just for a simple hello world. So let the compiler do that for you. So that's the -s file. You can see the assembly that's output from your high-level language, but we can't run that yet. So the next step is, okay, take the assembly and change it to binary. So in order to do that, we have to do -o for an object file, and we do, or not VI, G++. And then we specify the executable name, which can be anything. So if I wanted to be like Windows, I could do main.exe. And it spits out this main.exe, which is just this instructions converted into binary. So if we do main.exe, prints hello world. It executes now because it's binary. And if we actually look at what main.exe has in it, it's got a bunch of, like, it's got a little bit of readability to it, but yeah, not fun. So yeah, good luck. If you can program in binary, you're a genius. Come see me. You deserve a PhD right now. So yeah, so this is the abstraction you're used to. You have high-level language. You compile it into an assembly code. Then from assembly, it's encoded into binary or decoded into binary. So yeah, so this is what we're going to be doing this week in lab. We're going to have, I'm going to teach you how to write some C++. It'll be guided with a documentation or something. Hopefully it'll be something fun like last week's lab with where you're making biscuits or something fun. And then you'll write a makefile that compiles it and everything for you, and then allows you to do these things and have fun with it a little bit.